So, hello everyone, and welcome to our 10 o'clock session named Fault Tolerance. It will be given by Gautam and Yuli Yang from Google. Are you guys online?
Yes.
Perfect. Oh, I can see you now. And before I hand it over to you guys, I won't to steal much of your time. Their affiliation, Gautam and Yuliang, are with Google, who recently joined the TAP activities, and we're looking forward to hear from you guys about fault-tolerant clocks and the vision and progress looking forward. So Gautam and Yuliang, over to you.
Thank you, Lal.
Are you able to present the screen, or will you? No, that's my screen. Will you be driving your screen?
We were actually hoping that you will present the slides.
You got it, you mean? Or you need me to? Okay.
Yeah. We would like you to present, but
Perfect. I will do that right away. Um, can you take the control of my screen? Can you see my screen? Here you go. That should work now. Sorry?
I'm not able to see the slides, unfortunately.
You're not? But it's a PDF. Just give me a second. Can you come over and do that for me? Are you able to screen the screen now? Here you go. Okay.
Yeah.
Yuliang and Gautam, the floor is yours. I'll try to extend it and you'll start talking.
Can we go to the next slide, please? Hi all, I'm Gautam, and together with Yuliang, we are going to present the design for Sundial, which is a hardware software co-design for next-gen fault tolerance capabilities for PTP. The agenda for the talk is as follows. We are going to introduce the notion of time uncertainty bound, which is a guarantee on the worst case error bound, and why in the context of data center applications, we need this bound to be as small as possible. We are going to discuss some types of failures that can occur in data centers and how they impact clock synchronization. With this background, we are going to present the design of Sundial, which is a hardware software core design. We are going to talk about some of the practical considerations, discuss some evaluation results before we end the talk with a call to action. Next slide, please. There are several applications of synchronized clocks in the context of data centers. Perhaps the most important or the most common one is to use time for providing consistency in distributed databases. Examples are the TrueTime API that is used by Spanner at Google, and a similar notion of uncertainty is used by Farm by Microsoft. There are other applications of clock synchronization as well, including network telemetry, one-way delay measurement for congestion control, and they're bound to be more if synchronized clocks with tight error bounds are available in data centers. Next slide, please. Applications such as distributed databases don't only need precise synchronization. What they need is actually a guarantee on the worst case error in the value of current time, because they use this guarantee to order transactions to provide consistency. And this metric or this guarantee is typically called as time uncertainty bound and is different than the abstract notions of precision or accuracy that are typically talked about in the context of clock synchronization. Failing this guarantee, database errors can occur, either in terms of incorrect or inconsistent data. To understand the importance of this guarantee or time uncertainty bound, also known as epsilon, let me walk through a simple example. Wait is a common operation that is used for ordering purposes in distributed databases. And let's say server one wants to read a shared variable x at timestamp t. And in parallel, there is a write also happening on this shared variable x, but at timestamp t minus 1. Now, if the clocks between server 1 and server 2 are not closely synchronized, timestamp t minus 1 at server 2 may actually be later in time than timestamp t at server 1. And therefore, to account for this sort of race condition, server 1 has to wait for a sufficiently large amount of time to wait out the uncertainty before it can actually return the result of the read variable x. And how long to wait? This essentially is determined by the time uncertainty bound, and it directly affects the transaction commit latency. Next slide, please. Next slide, please.
It's coming. Here you go.
Thank you. So then the question is that why do we need to make this time uncertainty bound smaller, right? So if we were to look at the rough latency breakdown of a transaction in these databases, we have the network portion, we have the processing portion, typically governed by CPU and memory latencies, and then we have this time uncertainty. And while technological advances such as RDMA, SmartNICs, NVMe have lowered network and processing times to single-digit microsecond level, time uncertainty bound has not received the same level of attention. And therefore, we designed Sundial that can provide around 100 nanoseconds time uncertainty bound, even under failures, which is 2 to 3 orders magnitude better than existing designs. Next slide, please. To motivate the design of Sundial, let me briefly walk through bare bones essentials of clock synchronization. So the very first step is to measure the offset between two clocks through timestamps and half RTTs. And then synchronization occurs over a path of devices. And for the purposes of this talk, we are going to restrict our attention to boundary clocks where synchronization is essentially occurring hop by hop. Then time is distributed in a data center, typically via a spanning tree. And then synchronization occurs periodically to account for the oscillator drift that can occur over time. Next slide, please. To give a more mathematical representation to time uncertainty bound, it basically has two components. One is the max drift rate, which is affected by frequency related aspects. And in terms of failures, these can be cooling failures or voltage fluctuations that can occur in data centers. And then the second component is the time that has elapsed since last synchronization. And this not only depends on the frequency of synchronization, it actually depends on things like connectivity failures as well, because if it takes really long time to recover from such a failure, this number can become very large. So in the next two slides, I'm going to talk about these two in a little bit more detail and come up with two design principles that will motivate the design for Sundial. Next slide, please. So in terms of the max drift rate, what we observe is that these systems actually set a very conservative value for max drift rate. And this is to account for the worst case drift that can be induced by the oscillators amidst the frequency and amidst cooling and voltage fluctuations. And as an example, Google True Time in the Spanner paper talks about using 200 ppm as the max drift rate. And while newer oscillators have vastly better thermal and voltage characteristics, we find that another way of compensating for the oscillator disparities is to do very frequent synchronization. So we are thinking of lowering the PTP message frequency to a very small number, less than 500 microseconds, for example. Next slide, please. But synchronizing frequently is not enough, right? Essentially, especially in the presence of failures. If the time to recovery grows by 100 times, the time since last synchronization can grow 100 times as well, right? And what is worse is that when it comes to uncertainty or the worst case error bound, it doesn't matter if a failure is occurring at a given moment of time or not. Hosts and NICs have to always report a very high value just because of the possibility of a failure occurring somewhere else in the network. because they don't know whether they are continuing to synchronize to the grandmaster or not, as an example. And yes, this is in the context of boundary clocks, but we observe that we basically need fast recovery from connectivity failures if we want to put a bound to the time since last synchronization. So with these two design principles, I'll hand off to Yuliang to walk us through Sundial's design and conclude the talk.
Thank you, Gautam. Um, Next slide, please. Yeah, this one. Yeah, so we designed Sundial to enhance PTP with fault tolerance based on the hardware-software co-design. So it can provide two key features that I mentioned before. In hardware, we build into it the message sending and processing, and also the failure detection. So all the synchronization operations can be done in hardware, so we can do that very frequently. After the hardware report a failure, it will report to the software that is local in the device. And the software will immediately enable a backup plan by reconfiguring the hardware to resume the synchronization. The whole process is very fast because it's local in the device, so it can recover the connectivity failures very fast. The backup plan is pre-computed by the controller, which is remote, so it may take a longer time. But it's not a problem because it's not on the critical path. Next slide, please. In the hardware, we provide three key features: frequent messages, fast failure detection, and also the remote failure detection. The remote failure detection is very important because it lets every node to notice whether it is still synchronizing to the grandmaster or not. Let's look at how the three features work together in practice. During the normal time, the grandmaster will periodically send messages very frequently, around every 100 microseconds. Then all other devices only send messages synchronously, which means they only send a message out when it receives one. So they don't send messages spontaneously, only the grandmaster do. And this is very helpful because they can help all the devices to detect any failure that can stop the synchronization from the grandmaster. For example, in the middle figure, if the link goes down, then the whole subtree all stop receiving messages. So after a short timeout, they all get notified that there is a failure that stops the synchronization from the grandmaster. Then, to recover from the failure, all of them in the subtree will turn to the backup parent for each of them. And this backup parent is pre-computed by the controller in a way that it can reconstruct the spanning tree to resume the synchronization. So now let's look at how the controller pre-compute the backup plan. Next slide, please. The backup plan have one backup parent per device. And since we have a very large topology, so there can be many choices for choosing the backup plan for each device. And also because the device cannot distinguish different failures. So we have to choose a backup parent that is generic to different type of failures. For example, on the left, the node on the bottom of the topology has two options for choosing the backup parent, denoted by the red arrows. But we show that option 1 is not generic. Although it works for the link failure on the top, it doesn't work for the node failure on the bottom. On the other hand, option 2 works for both failures, so it is generic. Next slide, please. And to be more specific, the backup plan has to be generic to any single link failure, any single device failure, and the root failure, which is a special case. And beyond any single failure, there can also be concurrent failures caused by some fault domain failure, such as rack pod power goes down, and they can bring down multiple devices simultaneously. In this talk, I will only cover the root failure and the fault domain failure, but you can refer to our white paper for all the details. So the backup plan not only have the one backup parent per device, as we mentioned before, It also has one backup route to handle the root failure. Next slide, please. The backup route will elect itself as a new route when it detects that the old route fails. So here the key question is, how does the backup route distinguish root failure from other failures, which is not straightforward. For example, in the two figures here, the blue node is the backup route. And on the left, the link goes down, and on the right, the route itself goes down. But the blue node will observe the same effect. That is, it stops receiving any messages. So the key question is how to distinguish root failure from other failures. The key idea is to get independent observation from other nodes. For example, the triangle here, they can get synchronization from the root along a path that is independent from the backup route. So even if the link goes down, they can still receive the route. So we can set up the backup parent of the blue node to an independent observation node, so that so the blue node can continue receiving message after turning to its backup parent along the path that goes through this independent observation node. On the other hand, if the root itself goes down, then there will be no message in the whole network, since only the root can spontaneously send messages. Based on this difference, we can let the blue node to identify the root failure using a second timeout. So essentially, on the first timeout, it will turn to its backup parent, and if it continue receive no messages, then the second timeout expires. Then it knows the root is down. It will elect itself as a new root. Next slide, please. Beyond the root failure, we also have to handle fault domain failures. This is important because if one failure breaks the connectivity of one node, then the node will turn to its backup parent. But if its backup parent also goes down, then it also goes down because of the same domain, then the failure is not fully recovered. So we have to avoid this case when computing the backup plan. Next slide, please. In evaluation, we run different schemes in the testbed with more than 500 servers and more than 200 switches. And we compare with different other clock synchronization schemes. Since they don't provide time uncertainty bound, we also enhance them with the calculation of time uncertainty bound. And we evaluate under different scenarios, including during the normal time when there's no failures, and we also inject different type of failures. Next slide, please. During the normal time when there's no failure, we show that with Sundial, it can enhance PTP with fault tolerance. So it can provide 2 orders of magnitude lower time uncertainty bound compared to other schemes. Here we show the distribution of the time uncertainty bound of different schemes. And we can see that even the maximum time uncertainty bound is only 43 nanoseconds with Sundial enabled. Please note that this is the case, there's no actual failure. But all other schemes, they still have to report a high uncertainty bound. Although they can provide a very good accuracy or precision, but since they cannot notice the failure that is remote, which can stop the synchronization from the grandmaster, so they always have a high uncertainty. Next slide, please. Then we also look at the behavior under failure. Here we plot the time series of the time uncertainty bound around the instance of failure. And then we show that with Sundial, it also improved the time uncertainty bound by more than 2 orders of magnitude. Next slide, please. So let's understand how the different techniques of Sundial improve the PTP progressively. Starting from the baseline PTP, which has a relatively high time uncertainty bound because its default synchronization interval is long. Then after we run the synchronization message very frequently, we can immediately reduce the bound by more than 1 order of magnitude. But we cannot reduce it further because all the nodes cannot detect failure that is remote, and which can break the synchronization from the grandmaster. So that's why they have to always report a high bound to prepare for the worst case. So after adding the synchronous messaging, which help all the nodes to detect such failures, then they can safely report a very low bound when they don't detect any failure, and only report a high bound when failure happens. Finally, after adding the backup plan, which completes the design of sundial, it can recover the failure very fast, so it can keep the bound at a low level consistently. Next slide, please. We also show that sundial can improve different application performance. For example, in Google, for Google Spanner, we show that it has 3 to 4 times lower commit wait latency. And with Swift congestion control, it can have 60% higher throughput under the reverse path congestion scenario. And we are also working on many more applications based on sundial. Next slide, please. So to conclude, we have built sundial to enhance PTP with fault tolerance. And with that, we built the first system that provides around 100 nanosecond level time uncertainty bound. And we show improvements for many real applications. Next slide, please. Yeah, so next slide, please.
Yeah. Sorry, was a mistake.
Yeah, so,
This one. Oh.
Yeah. Everyone, please feel free to check out our paper, which was published in OSDI last year. And also, you can find more details on our TAP project webpage. And there are many talks and other details. Thanks for the listening.
Thank you, Liang and Gautam. There is a question, and I'm going to direct it to Dutan. Please go ahead.
Hi, Yulang. Gautam. Thank you for that inspiring talk. I want to ask two things. Do you see any advantage in enabling an hardware for dynamic error-bound calculation? Because as I understood today, it's relying on the worst case of the worst cases. This is the question number one. And second, would you think that it would be helpful if the hardware will maintain also the error bound of this specific node and it will not be have to calculate it by software?
I will repeat the question. So the first question, do you guys see a need, a call for a hardware-based calculation of the error bound?
Yeah, I can take these two questions. Are you able to hear me?
Yeah. Thank you.
Okay, great. Yeah, so I think that's actually a very the first question, whether we should do some hardware based reporting of the error bound or not. I think it's a very good question, and we actually when we are kind of prototyping or building this up, went back and forth on discussing it. I think the hardware does add a layer of accuracy. In a layer of accuracy in the uncertainty measurement, right? The other way to go about it is to kind of have it propagated in the packet format, right? At least the per hop inaccuracies in the PTP packet format, and then the final hop can be computed by the application itself. So I think there is value in kind of the hardware being able to provide the uncertainty calculation by itself, because it really has the best measure of time since last synchronization, for example, and so on and so forth. Coming to your second question, I think it actually comes to around the traceability aspects of PTP, especially when we are using boundary clocks versus transparent clocks, right? In boundary clocks, if we want to measure our divergence from UTC, the best way is to kind of propagate this error bound in the PTP packet format itself over the series of devices. And in transparent clocks, that problem is slightly simpler because you are directly querying the
with the master.
With the master, although you are kind of correcting your timestamps on the way. but that is the way to go in boundary clocks because divergence to UTC is definitely a very important metric for clock synchronization use cases as well in data centers.
Thank you.
Google friends, do you want to say anything about time sync reliability and your plans forward?
Yes, we are going to start a work stream focusing on time sync reliability, covering some of these extreme fault tolerance use cases for consistent databases, UTC traceability and UTC divergence measurement, and a few other metrics that we are interested in. So we'll start this work stream early next year. So if you are interested, feel free to reach out to us and we'll get you on board.
That's amazing news, and we look forward to this work stream to come alive and with your experience and your expertise to guide this development. So thank you very much, Gautam and Yuliang. We're getting to the next session.
Thank you.